Thank you very much. Okay, now we would like to go on to the next. Part 5, Would I Talk in Discussion? So the stage is ready. We invite the first speaker, Dr. Gregory Wiberty, CEO and the Vice Chairman of the Board of ID Quantic, Switzerland.
Good morning, everybody. この度、UQCC 会議にお招きいただき講演の機会を私に会っていただいた主催者の方々に感謝いたします。日本の量子技術のリーダーシップと長年の取り組みは印象深く、この会議は非常に興味深いものになっています。ここからのスピーチは英語で行います。So I'm with the company ID Quantic, and we've been working in the field of quantum cryptography and quantum technology for now close to 14 years. The company was founded in 2001. And when we started, we were very enthusiastic because we thought basically, we were going to offer uncrackable communication, absolute security, and we thought surely this doesn't have a price, and commercializing this kind of technology is going to be easy. And what I'd like to do today with you is to share a little bit what we see on the market and the challenges that we face with bringing this technology to the market. First of all, I think there's good news because there's a lot of progress in the field of quantum computing, with companies like Google, IBM, Intel, Microsoft investing significantly in this technology. And we should remember that quantum cryptography offers long-term security even against quantum computing. So one of the motivations to use quantum cryptography is to be quantum safe. The classical cryptography community has noticed this kind of threat, and earlier this year in April, NICT in the US organized the first workshop on cybersecurity in the post-quantum world. I must say, as a physicist, I'm not sure what a post-quantum world is, but the topic of the meeting was to discuss quantum-safe cryptographic techniques. And more recently, the National Security Agency in the US made an announcement in August of this year where they announced plans for transitioning to quantum-resistant algorithms. So there's definitely a trend, a revolution to quantum-safe techniques and communications. Well, what do we do today? Well, I'll show you here an example of a hybrid system similar to what NEC showed earlier today, where two data centers are connected by a quantum key distribution system, as well as classical network encryptors doing AES encryption using the keys provided by QKD. And the goal here is to achieve long-term security by using these quantum-safe keys. There are several deployments in Europe and in the banking and government sector, and a typical type of application now you see is on the top left, banking sector, where bank buildings are connected point to point and secure communication is established. Challenges that we face are that often the installation of optical fiber may be expensive, and also due to the nature of the point-to-point nature of QKD, routing data across multiple sites is difficult, as well as the challenge to connect remote locations. And the vision here is to transition to trusted node-based network. There are several projects worldwide. We hear more about a project in the next talk. But the idea is to build a network, a backbone network, connecting trusted nodes and endpoints so that multiple facilities can be connected securely using these QKD devices. And the idea, for example, for the same bank, now can connect all the sites. This could also have application in the industrial sector where, for example, manufacturing data or intellectual property data is protected, as well as we've heard as the use for genetic data. So we have, there's progress, and you see here a picture of our newest QKD system, which will be displayed at the exhibition next door. It's our 4th generation system. It's a rackable system with the idea that a trusted node can consist of several of these systems in a rack. So there's progress with quantum technologies. There is growing awareness about the need for quantum-safe cryptography, but that we still face a challenge. If you look at the program of this NIST workshop, it lasted 2 days, 25 talks, 2 panel discussions, and not a single talk on quantum key distribution. Quantum key distribution, was just briefly mentioned in one of the talks. This means that the classical cryptography community doesn't really see QKD as a viable option. Another example of this is a slide shown by Dave McDrew, which is the chief cryptographer at Cisco at the same workshop, where he basically said quantum key distribution is not needed. And he was listing a number of factors. The first one, of course, minimum computational assumptions for QKD. That's a plus point for QKD, but then a number of no's. Now, of course, if you look at these, he's comparing the apples and oranges. Not all the criteria are relevant. I think what we should really look at is use case based. For different use cases, different assumptions are needed, and as well, not all of the criteria are relevant. But nevertheless, I think as a community, we face a challenge of getting a fruitful collaboration with the classical cryptography and information assurance community. And as a conclusion, I'd like to propose that we stop talking too much about technologies, about quantum key distribution, or about quantum-resistant algorithm. That's the other alternative. But we focus at benefits that we offer to users, which is quantum-safe long-term security. And it's very likely that in the future, a quantum-safe solution will require a combination of technical approaches based on physics and mathematics. And I think we need more initiatives to foster a dialogue between the different communities, such as the ETSI Quantum Safe Cryptography Workshop, which led to a white paper, or the Quantum Safe Security Working Group set up last year at the Cloud Security Alliance. With that, I'd like to thank you for your attention. And I'll be happy to answer questions later at the discussion break. Thank you.
Thank you very much, Dr. Gregory Ribody. Now, we'll invite the next speaker, Professor Chan Zhang from the University of Science and Technology of China.
Good morning, everyone. Here I would like to talk about the quantum network in China. Okay, so here are some examples for the worldwide quantum network, DARPA network, the Europe network, the Tokyo network here, and the IDQ network in Switzerland. In China, Hefei, we have a 46 nodes quantum network by Quantum CTEC. Jinan, we have 50 nodes, but in all these metropolitan networks, we use trustable relay. What's trustable relay? For Alice and Bob, if they want to share the key, they do the QKD with a relay point. And the relay point will do the XOR operation on his case and announce the result. Then Alice and Bob will share the key. Why we need a trustable relay? Let's go back to the Hefei network. You can see we have 46 nodes. We cannot do the point-to-point system for any 2 points. It's a waste of resource. So that we use 3 main, you can see, 3 main kind of trustable relay. So any 2 points, if they want to share quantum key, they use the relays. The relay is good because it makes things done. But on the other hand, it's the weakest point of the system. Because if the relay is dishonest, or the relay is like, if the relay breaks down, the system breaks down. This is the kind of the question of the metropolitan network. Meanwhile, even for the point-to-point system, it may be not secure, because QKD is in principle is secure, but because you are using realistic devices, so there may be some side channel for the devices, and there will be attacks. Recently, the most attack is on the single photon detector. Here are the attacks. So There are many countermeasures, of course, but there is one way to close all the measurement checks. It's called MDIQKD by Huai-Kuang Low Group in 2012. The basic idea is like Alice and Bob, both of them send the quantum state in the public measurement platform for the Bell state measurement. In this, even if the dropper controls this platform, she cannot get any information. So which means for the MDIQKD, Alice and Bob, they are using the untrustful relay. Here are some experiments of MDIQKD 2013, including our group. Several groups has done in the lab. And 2014, we moved it 200 kilometers, and also in the field test. So it's kind of, it can go long distance, at least for the metropolitan area. And actually, it's more than good for the network. It's MDIQKD is like, it naturally fits the star type network. Think about the Toshiba Cambridge 2013 Nature paper. In their paper, here, all the users in their star type network, and all the users, they using DWDM, they using optical switch, they share the one single photon detector, and then they do the QKD network. Why they want to share one single photon detector? Because single photon detector is the most expensive part of the system. So that for this for this kind of network, it's reduced the price, reduced the resource requirement. But of course, here you need to trust the single photon detector for if any two users want to communicate. And in MDIQKD, you just simply replace the single photon detector with the Bell state measurement station, and then you get an MDIQKD network star type and with untrustful relay. Okay, even if a dropper controls the measurement station, they cannot get any information. So that's our solution. And so we pick up four nodes in the Hefei network. And you can see this U1, U2, U3 are three users. And the R is the relay. Inside of a relay, there will be an optical switch. And it can switch to any two users to the Bell state measurement. And then the whole area is about 200 kilometers square. And okay, here are the key rate result. And generally, we get about 30 bit per second. This one is kind of good for the message for the area. But of course, if you want to get a video, you can probably use the AES amplification, or you increase your hardware, go to some 10 gigahertz system. I think it's possible. And how about the long distance? We can kind of fix the metropolitan, but for long distance, we have two solutions. One is called the quantum backbone line, or main trunk line. It's also like from Beijing to Shanghai. It's what we are doing at 2,000 kilometers, and we have about 30 relays, and the total length is 2,000 kilometers. And the customer is the China Industrial Commercial Bank and other agencies. Of course, here we are using the trustful relay. And for this project, we have three phases. And The phase one is a protest of quantum product. It's already ended for the last April. We put a public announcement, and we invite IDQ, Quantum CTEC, QRSky. Anyway, IDQ didn't go, so Quantum CTEC get the approval. Now we are doing the indoor system debugging. You can see that here is the indoor system debugging. We are doing some certain nodes inside of the room and to do the debugging. And the phase three is the deployment. We're supposed to finish this project in the end of 2016. And if you do not like this idea, the second solution is the satellite. We will launch a satellite, like Professor Arno Zillinger mentioned, in the beginning of next year. And the whole project is led by Jianwei Pan. And if you are interested in the MDIQKD network, if you are interested in the relay, the main trunk line, and also the satellite, you are welcome to attend the Trustworthy Quantum Information 2, July, USTC Shanghai. Thank you.
Thank you very much, Professor Chan Zhang. Now, we invite the next speaker, Dr. Mark Esler, CEO and CTO of Princeton Lightwave Inc., United States of America.
Thanks very much, and good morning. What I'd like to describe today is some work that we're doing at Princeton Lightwave, which is a company near Princeton, New Jersey in the United States. where we're focused on semiconductor single photon detectors and the use of this detector technology to solve some of the most pressing problems that we see coming in the next decade or so. In terms of exponential explosions that we're seeing in new technology, I think you've heard a lot this morning already about the dramatic increase in connectivity between devices and the emerging autonomy of these various devices. To achieve this connectivity, we need to distribute information, and autonomy is achieved by collecting the necessary information which can then be processed to have autonomous behavior. So in terms of connectivity, this distribution of information needs to be achieved with very high performance and with security. You've heard a lot this morning about the challenges of increased connectivity and the absence of privacy. And this goes beyond just standard devices that you think of when you think of connectivity, like smartphones and tablets and computers. We've seen notions of how our homes and our offices and even our entire transportation systems are going to be networked. And so you have a paradigm shift now to an emerging Internet of Things. In terms of autonomy, these devices need to collect information to achieve environmental sensing, which is then used to process that information to gain situational awareness. Again, you've heard this morning already about platforms like drones, autonomous cars, and robots. These are technologies that are going to become ubiquitous over the next decade, and having the right technologies for sensing is going to be critical. Now, in terms of the evolution from 20th to 21st century technologies for distribution and collection of information, what we're seeing is a paradigm shift from radio frequency, where in the last century you had signals carried on copper wires. Those are now moving towards photonic solutions. You now have lots of communication that's carried on optical fiber. In the same way, you have many radio applications moving to free space optics, and you have traditional radar moving increasingly to LiDAR techniques. Really, this is driven by the fact that optical technologies have an information capacity that has orders of magnitude more capability than radio frequency. And in terms of maximizing the efficiency and minimizing the power requirements for these optical technologies, the use of single photon detection is very often critical, and that's been a driver for our work in this area. So in terms of connectivity with photonics, really the end of the last century saw the deployment of enormous capacity in fiber optic networks. What we see coming is different kinds of links that are getting off the ground. Several months ago, the journal The Economist published an article about expanding the internet, which they have now dubbed Sky-Fi as a generalization of our already very commonplace Wi-Fi. And what you'll have is helium balloons or solar-powered drones or low Earth orbit satellites. These are the kinds of platforms that are being pursued by high technology companies like Google and Facebook and SpaceX, and the list goes on. And it's going to change the nature of communication the way we know it. Now, at Princeton Lightwave, we're working with NASA's Jet Propulsion Lab in going even a step further. NASA would like to demonstrate free space optical communication from deep space, so over interplanetary distances. And in some sense, this use of single photon technology to achieve interplanetary communications is sort of a first step towards optically networking the solar system. Now, the whole focus of this conference, or at least a large part of it, has been on security and privacy and the use of QKD to achieve that. There's no need to point out in the last century, really, we secured information simply by locking it up. That's no longer an option now with the increase in connectivity between devices, and so we need solutions to have accessibility with security. And you've already heard a tremendous amount this morning about the potential for QKD. And one of the most critical elements of those QKD networks is the single photon detector. And that's an area where Princeton Lightwave has been focused for the last decade because it is one of the key challenges for establishing high performance QKD. Now, I also mentioned another emerging trend towards autonomy of devices. Really, here what's going on is that we're replacing human sensors and computing with robotic sensors and computing. And one of the industries that I think is due to be revolutionized in this way is the automotive industry, where we will have true automobiles in terms of autonomous mobility. And we'll need very sophisticated sensors on cars in order to accomplish that. Passive optical cameras and radar are already existing technologies. Increasingly, LiDAR is now being used as the optical equivalent of radar with much higher resolution, three-dimensional capability. And so that's another area that Princeton Lightwave has been focused on. Can we use our single photon detector technology to enable LiDAR that outperforms all other technologies in automotive? As a final example of what we've been doing with single photon sensitivity, we've developed 3D imaging cameras based on this LiDAR technique, where environmental sensing is now possible from very high altitudes, 25, 30,000 feet or more. I show here an image that was taken by Harris Corporation, which has announced a new service to provide very wide area aerial mapping. And one of the benefits that this single photon camera brings to them is they can now collect this data 10 times faster than any other known LiDAR technology. So just to sum up, again, my theme has been that the connectivity of devices is driving advances in distribution of information, and that single photon technology is a critical capability for achieving high performance and security. And in autonomous devices, the collection of this information with single photon sensitivity is enabling dramatically new capabilities. Thanks very much.
Thank you very much, Dr. Mark Esler. Now, we invite the last speaker, Dr. Andrew Seals from Toshiba Research Europe in Cambridge, and the chairman of the ESTI Industrial Specification Group in QKD.
Thank you. Well, I'd like to tell you about the work of a body I chair at ETSI, the European Telecommunications Standards Institute. And we're forming the first industrial standards for quantum communications and for QKD in particular. Now, in recent years, there have been really remarkable progress made on deploying networks for quantum key distribution. And we've heard this morning all about the Tokyo QKD network that's been created by the Secure Photonic Network project of NICT, which we've been involved in with several other companies as well. Also, Dr. Zhang has just told us about the networks, the metropolitan networks and the long-distance links that are being built in China at the minute. Some really remarkable advances there too. There are also very ambitious projects proposed in South Korea and also in the USA, which ID Quantic are involved in. And recently in the UK, there was an announcement of a new quantum technologies initiative of £270 million. And as part of that, the Quantum Technologies Hub in Quantum Communications is building a quantum network in the UK, which we're involved in, along with British Telecom and several universities in the UK. So with all of this activity going on at the minute, making pilot deployments for quantum communications, it's really meaningful now to define what the requirements are for users and to develop industrial standards so that all of these networks can communicate together in the future. So why do we need industrial standards? Well, industrial standards are essential, first of all, for the interoperability of systems from different manufacturers. So that means a network provider can source their equipment from different manufacturers and be assured that those systems are going to work together. That's a good thing. Also, manufacturers know that they can sell their systems all over the world and not just in one region. So everyone wins from that, those standards. Then standards are also very important if we want to integrate QKD into conventional telecom networks. And this is something that we think is very important for accessing large markets for QKD. We need to have agreements on things like how we provision the quantum and the ordinary data channels within the network, for example. Standards are also very important for stimulating application development, so they can define a common interface on top of the QKD hardware, which can be used then by application developers to develop their applications on top. And they'll know that their applications will work with hardware that's supplied by different manufacturers. So it can stimulate the creation of new applications for QKD systems, which is very important. They can also stimulate a component supply chain for quantum technologies, components such as single photon detectors that Mark has just been talking about, for example. So again, this is very important. If we have well-defined interfaces for these components, then we can have interchange of components from different manufacturers within the system, and that can stimulate the supply chain. And finally, and also very important, standards offer security assurance to customers. It assures them that QKD is fit for purpose and has been implemented in a secure manner. So this is what the ETSI Industry Specification Group, ISG, in QKD are working on. We have a membership which comprises many different bodies, from large companies, telecom operators, SMEs such as ID Quantic, for example, NMIs, those are national measurement institutes such as NPL in the UK, PTB in Germany, INRIM in Italy. Also government labs and academics from universities too are making a very valuable contribution to that body. And since its conception in 2008, it's published a number of group standardization documents on various aspects of QKD and quantum communications. And let me say also that new members are very welcome to come and join this body. So if you are interested in contributing to making industrial standards for this technology, please get in contact. So the current work of the ISG are in things like deployment parameters. So how to define user requirements for, or what are the user requirements for implementing QKD, and how we define a common language between the supplier and the user of the technology. In the specification of quantum components, so what parameters are important for quantum components, such as detectors, sources, and modulators, and how do we measure those parameters? We need a common way of doing that. And also, what impact do those parameters have upon the security of the system? This is also very important to consider. And a particularly important area, I think, is the area of implementation security. So to ensure that the implementations that we have are secure and robust against attack. So just to say a bit more about that, we know that in theory, quantum key distribution is unconditionally secure, or perfectly secure, in other words. But in practice, no real system can really match the idealized model of the theoretical system. There are also always some small deviations between the real system and the idealized system. And this gives an eavesdropper, Eve, some potential ways to attack the system. Her attack could be a passive one, where she just gains some information about the secret key by measuring some information that is unintentionally encoded upon the single photons sent by the sender Alice. Or she could launch an active attack, where she makes some type of attack upon the system. So our approach to dealing with this implementation security within the ETSI group is, first of all, to catalog the known attacks, which are known at the minute, then to introduce appropriate countermeasures against those attacks, if we can, and finally to reduce Eve's residual information after these countermeasures are introduced, using privacy amplification to be as small as possible. And to give one example of that, here is a slide that describes the Trojan horse attack. So in the Trojan horse attack, Eve shines some bright light into either the quantum transmitter or the quantum receiver, hoping to gain some information about the signal states prepared by Alice from the weak back reflections which come from that strong light. Doing that, Eve might determine some information about Alice's settings without causing any disturbance to the single photons, and therefore go undetected while gaining some information about the secret key. And in this case, we have a very simple countermeasure, which is just to add some passive components to the system, some optical attenuators, optical isolators, and filters. The isolator is a device which allows the photons to pass out of Alice, the quantum transmitter, but strongly attenuates any light which is sent into Alice. And we've shown that if we can provide sufficient optical isolation of around 170 dB, then we can strongly limit the amount of back-reflected light to be less than 10 to the minus 6 photons per pulse. And in that case, we can use privacy amplification to reduce the amount of information known to Eve to be very small, while causing really only a very small reduction in the secure key rate. As you can see in the graph here, it really only affects the secure key rate at the very longest fiber lengths, with negligible change in the key rate for shorter fiber lengths. Okay, so finally, just in summary, recently there have been several large deployments of QKD networks, and so now is the time to define industrial standards. And these are essential for ensuring future interoperability of different systems, to assure customers that the technology has been implemented securely, and also to stimulate markets for components within those systems, the systems themselves, and also the applications which are developed on top of the systems. So thank you very much for your attention.
Thank you very much, Dr. Andrew Seals. Thank you very much for all the speakers. Now, we would like to invite Dr. Sasaki, Mr. Shimamura, and Dr. Toyoshima to the stage again and move on to discussion session. So we would like to have questions from the audience. Dr. Sasaki, please.
Okay, so in this discussion session, all of your audience and speakers can discuss any hot topics or any urgent issues. So I'd like to first have any question from you, mainly for these for speakers. So do you have any questions? Please raise your hand. Vadim?
So I would like to, this is what I'm going to ask is not my question. It's a very embarrassing question I got from one of British classical cryptographers. And the question was the following. We did a presentation about point-to-point UQCC via a satellite link, and then he asked, why don't you just give Alice and Bob a hard drive filled with random numbers? It's going to be cheaper and more longer key than you could generate over the entire lifetime of the link. And I didn't have a good answer to that question. I could think of some weak arguments, but do we have like a really good answer why QKD makes sense when you can't just pre-distribute random numbers on storage media?
I guess that is a valid way of distributing keys at the minute. In many circumstances, actually, people don't use public key cryptography. Rather, they use physical transfer of the keys, especially for very high security applications. But I think there are advantages of using a technology like QKD, an automated technology. It means, for instance, you don't have to trust the courier, which is delivering that key to the other side. And although you can put a lot of key material on a hard drive, we can also deliver a lot of key material through QKD, and we can also frequently refresh that material too. So clearly there are advantages of doing it in an automated way, such as QKD. Anyone else like to add something?
Vadim, one other element is the fact that you can produce fresh key and with QKD, and having a key produced just when you use it is definitely an advantage in terms of security, because if you store a lot of key material, this is also a loophole, which you could leak this key and which can be a problem. So the ability of live key generation is a benefit.
Are you satisfied with this? Okay. Okay, please. This guy.
I think I had the answer, but I think it wasn't clear. The basic difference between what you propose and the QKD is that you'd never be sure that there is another hard drive with the same data somewhere else. So, and the quantum case, you can be sure that if you create it now, there is any copy of it. So it's completely different. I don't think there is any equality, I think this should be solved this way. In German, in Second World War, you can be sure that no one will listen if you use quantum cryptography.
Okay, thank you. Okay, any other questions? Okay.
I'm continuing to answer the first question, which is very often asked by classical cryptographers. And it's not so easy to answer because of the need for the users to authenticate each other, to know whom you're talking to. And it's been pointed out that if you say that the advantage of quantum cryptography is that you can distribute fresh key, there's a little weakness if there is a man-in-the-middle attack who has observed your key so that you lose the ability to authenticate whom you're talking to. However, that is a smaller weakness than the danger that your large volume of previously shared classical key would be compromised. It could be compromised without your knowing, and then for the rest of the life of that key, your communications are insecure. With quantum key distribution, if you break into it once with a man-in-the-middle attack, then you have to continue operating the man-in-the-middle attack continuously. If you forget about it for one day, then the privacy is restored. So I think that's a little stronger answer. Even if the QKD never gets to be never gets to have such a high key rate that it is competitive with sharing a hard disk. It still has this extra security in that it can, in order to compromise it, it needs a continuous attack rather than just a one-time attack.
Okay, thank you, Charlie, for your very useful explanation. Okay, do you have any other questions? Maybe even you can ask in Japanese. Okay, so maybe you guys, for speakers, do you have any question to each other? Maybe, we have a fiber network and Toshiba, ID Quantic, NEC start to, sell the products maybe soon. But for example, Andrew, can you tell us when will be likely?
Likely to sell the
Yes.
QKD? I was hoping you wouldn't ask me that question, actually.
Okay.
Be very careful in the
Yes,
answer
yes,
to
I
that.
know.
So
But try.
Yeah, so we're not selling the QKD system yet, but I guess what we're doing at the minute is we're preparing for that eventuality. So we have to test the market because we want a product that is really has the right attributes for the customer and will deliver them a good user experience. So that's what our business groups are working on at the minute. And the result of this exercise will determine whether we launch a product or not. But at the minute, I can't give you a definitive date for that, I'm afraid.
Wise answer. Okay. How about Gregor? Maybe you have been selling certain amount of QKD systems.
Yeah, so we've been selling this kind of system for several years. I think the first real deployment we did in 2007. We've then been selling to governments and banks in this hybrid AES QKD type of scheme. Very important for us was to combine this with IT grade technology. The encryptors are typically products that IT managers know about. So if you tell them that you offer a complete solution based on these encryptors, they're more comfortable to deploy QKD technology in their networks. And so this is a commercial product. We've been hit a bit by the global financial crisis with banking customers slowing down in their investments, but we see that coming back last year and this year. So I think there is potential. Of course, as a small company, we don't need a market as big as Toshiba to make we're probably more agile and can address smaller markets. And that's why we started earlier, probably.
Okay. Do you have any plan to sell your systems to China? China is making a very big trunk lines, and Shenzhen need lots of QKD systems.
Okay. Actually, as I mentioned in my talk, for the main trunk line, I asked IDQ to send their system for the testing. But of course, for this main trunk line, we're planning to use the decoy state system. And since you guys didn't do the decoy, you are working on COW. So that's a pity. But we have a plan to purchase one COW system, but for to just like what you did in the Tokyo network, we want to buy it in Shanghai in the control center to show that different kind of network, and we didn't plan to put it in. We didn't plan to put the COW system in the main trunk line, but probably we can put it in the local network, Shanghai network. That's the one thing. And in the future, I think we may have some plan to build different network and the main trunk line, and also some private companies are going to the field to want to build some main trunk line, and I think IDQ or NEC or any other quantum product provider may have the chance. Yeah, but I don't know. Probably you need to consider about the system. Is COW? I don't know. You need to think about decoy. I don't know. Yeah.
Okay, thank you. Do you have any other questions? Okay, here there.
This is a technology that impacts very heavily on the privacy and security of the citizens, so your researchers and manufacturers. But which role can you see for political institutions in this? You expect political institutions to help you as early users, early adopters, or as technological facilitators, or in the development of standards, or so? I don't see any involvement of political governments in these kinds of issues. What do you expect the political counterpart to do in this field?
Okay, maybe. Well, in Japan, we are starting a kind of a regular meeting with relevant ministries, which are working on the mission-critical applications. And users are still watching at the current status of QKD. Especially, they want to know how to certify the practical security, I mean the implementation security of the QKD systems by themselves. And they are mainly the specialists of RF communications. So they know electronic circuits and computer as well, but not necessarily the specialist on the quantum physics. So once we could establish a kind of a consensus, community-agreed consensus, they are really ready to touch our systems and start to learn. So now we are just working in that kind of directions. And I can say when, but maybe it's been 2 years or 3 years since we have been having such sort of a regular meeting. This is the status in Japan. How about in Europe? Or maybe in US?
Yeah, I think in Europe we have a similar situation, actually. There is an interest, but yes, of course, they want to see some more development of the technology, and especially in the area of implementation security. I think standards, they're more an issue for the manufacturers themselves and the users to develop rather than political entities. But we hope that governments can be some of the early adopters of this technology. And there is some interest in that at the minute.
If I may add something, policymakers could have a huge impact on this kind of technology, because we see in certain countries discussions about banning cryptography in general. And so, of course, if it becomes illegal to use cryptography, that will have an impact on quantum crypto. And that's why in some areas there's interest from the trusted node networks, which from a physicist point of view are not ideal, because you have this trust assumption in the middle and possible access to data. But actually it means that lawful interception can be implemented and guarantee then still to government some level of access.
Okay, any other questions? Okay, please.
Yeah, I have a question relating to Dr. Sasiki's talk about, I was very fascinated with the idea of using QKD and within a fiber optic network of a car, for example. But I would like to understand better how QKD would actually, help. Just recently there was a lot of news about people hacking into cars remotely, actually through. It turns out there were bugs in the system, right? There was no security implemented and so on. But what I don't understand is how QKD could actually help, secure such a system, and which is very sensitive, right? Because people's lives might depend on it. Maybe you can explain better how QKD would help in such scenarios.
Well, actually, intra-car network is a really long-term goal to which the QKD technology would be applied. So maybe in 10 years or so, maybe main issue is more like a cyber attacks to a wireless communication systems. But I think in the frontier of quantum cryptography and communications, quantum repeater technology or some quantum integrated circuits are very hot. And I think those technologies could be applied to the very new intra-car network in the future when harness system is all optical. So maybe quantum memories would be inside the car and store the secure key using the entanglement. Then we can really exclude the side channels which could have been introduced inside the car. But it's a really, long-term vision. So I don't know. There might be other solutions as well, but they're certainly one of the challenging goals in this direction. Okay. Okay. Any other questions? Okay. In the back.
Yes, as we can see, several countries are trying to establish quantum network, but based on trusted nodes. I think it is possible in technique, but of course, everybody knows it's possible, even though we didn't do that. So I'm thinking, should we wait for a while for the real quantum relay and to establish the real quantum network instead of based on the trusted nodes?
Do you have any answers?
I think a full quantum network, for instance, using a quantum repeater, is very difficult technology at the minute. Anything which involves quantum memory is going to be a severe challenge, I think, for many years. But maybe we can see some introduction of quantum technologies. For instance, MDI QKD is an example of that, for instance. So we can reduce some of the trust within the network, perhaps, in a shorter time than it takes to realize a full quantum repeater network.
The other thing is that something we shouldn't forget about is that in a real-world application, the transition to new technology will take a long, long time. If a government needs to deploy a secure network, just the simple network design, testing, what Professor Zhang has been doing, is something that you don't do overnight, even though you could buy technology. And so that's why some governments are starting to prepare now, because they need to have a quantum-safe vision. And if you want to prepare, what can you do? Well, today what you can do is use trusted node networks. And then, so of course there's this trust assumption, but nevertheless, based on conventional anti-tampering technology, you can get a good level of security in spite of this, assumption.
I want to continue to answer the question, because as I mentioned in my talk, that for the metropolitan, if you use MDI, you do not need any quantum repeater, right? And for long distance, we have two solutions. One is using transfer relay. Of course, it's not a good idea for physicists. But if you can build a quantum repeater now, okay, we will give up that project, but you cannot do it, right? And I think for the quantum repeater, it may take about more than I expect. Probably, I think, and so what can you do with the current state? You can use in the quantum satellite. That's a good idea, but it's very expensive, first thing. And also, it's not convenient. You should do it in the night, and the K rate is low. So why not just build the highway network, and someday, if possible, the quantum repeater works, okay? We just put the quantum repeater in the nodes. And we first build a network and people can use it. Why we built the so long main trunk line for the network? We have a belief that if you didn't build a kind of long line network, the long line network, if it's only local, I don't think too many people will use it. But if you can do, for example, in China, if you can only do QKD inside of Beijing, it may be lost interest. If you can do the secure communication between Beijing and Shanghai, it will be very, I think it has big value, and people will use it. It's just like the internet. If there is no global internet, if you can only visit the website inside of the city, they will be not very interesting. And for the future, I don't know, for the quantum repeater, even the quantum repeater is very good, but if it's low temperature, I still don't think it's a practical solution, but it takes time. Yeah, we are looking forward to a real one. Yeah.
Okay, thank you. Maybe let's discuss about the space network, and you are the users and you are the providers. Do you have any technologies you are interested in?
From a free space guy, and so I'm interested in the Princeton light wave sensors. Maybe in Japan, discussion on next generation communication satellite is going on. So which might use something lasercom from satellite to ground. So we want to use adaptive optical system for this in the future. Maybe within 5 years, we want to develop AO system for free space communication. So we need sensitive wavefront sensor for this. Maybe your camera can be used for sensing the wavefront, maybe. So in the future, we want to collaborate each other.
Yeah, I'm in the unenviable position of being the one guy much lower in the food chain sitting on this stage. But we have the same problem. You worry about how big the end market is for QKD. We have the same issue of where are the markets for single photon detection technology, and in many cases for a QKD network, you're able to reuse a lot of existing very good technology. So a lot of the components that you use today were brought up through much bigger markets in traditional communications 10, 15 years ago. What we're looking for is a way to continue advancing the detector technology in other areas and bring that benefit to the QKD community. And so, for instance, the work I discussed in LiDAR, we've found has been extremely useful in terms of improving the devices and then bringing that back to the discrete detectors that are used in QKD. And so I think it's the same with the free space optical communications. Our first generation of 3D imagers really were optimal for doing imaging, not for continuous monitoring of a single photon stream for communications, but we're now developing a next generation of imager that will have that constant free running capability. And so I think that what's key for us is to be able to address a number of different applications where our components and our modules are relevant, and that allows us to continue advancing that technology so that it will serve other markets that are not so big today, but we need to be there with the right components when they become big.
Okay, thank you.
We can be one of the users. Thank you.
Unfortunately, the time has come, and I'd like to close this part 5. Thank you very much.
Thank you very much for your great talks and discussions. Please give them a big hand. Thank you very much.